Okay, so we're getting started with data analysis. This is the finding speed of sound in the resonant tube experiment. So let's take a look at what we have data-wise. So we have frequencies. These are just numbers stamped onto the each tuning fork. Is this an A note? I think it's called A4 for anyone who does you know enough about if you played musical instrument. So is this a B4, I think? And I don't really know what the other ones are. C and D's, at least C and D, but may not be the D4. All right. So let's get started. We have frequencies, and we're supposed to be plotting out wavelengths as a function of 1 over frequency. So we already have the 4 frequencies. All we have left are the wavelengths that we're collecting data for. So this is that A4 um, tuning fork, and I started at this location. I started hearing the enhancement of the sound of the resonance, and then about 60, about 99. So if you think about it from the open end to this location, 18.7 is not exactly half wavelength, is not exactly quarter wavelength, it's a little bit arbitrary. So that's why we keep collecting more data, because we're pretty sure between this place and the next place, we have to fit in one full wavelength. That one full wavelength is down and back up. So that means we're increasing distance by half a wavelength in between the marks, right? Basically half a wavelength down, half a wavelength up in the sphere, and we can hear the sound loudly. So between these two should be half a wavelength, any two marks, right? We have 3 marks, that means another half wavelength right here. So what I did was I calculated the full wavelengths by subtracting the first mark out of the last mark, knowing that there is a full wavelength in between. So let me show the calculation right here. So I'm subtracting the 18.7 out of 99.4 and divide by a 1 wavelength, divide by 100, that is converting centimeters into meters. So I got a wavelength and it's short, it's 0.8 meters. So that's right. So basically between these two, there should be a full wavelength. That's almost the length of the tube, right? The tube has about 1 meter long. So that makes sense. And the next one has a really similar frequency, except that it's higher frequency. It means slightly shorter wavelengths. Because let's do this. I'll insert something here. Come on, I'll insert some text box. I'll actually just insert an equation here. So hmm, it's not just it's pretty small. Let's make it bigger. Okay, so we know this formula, right? Speed of any wave is frequency times wavelength. And the speed of sound in air is a fixed quantity. So any frequency will have the same speed. Otherwise, sound will start to disperse, which means when we're talking and someone else will hear our higher frequency first, if somehow higher frequency sound propagates faster, that will reach us first and the sounds will be distorted. Right, yeah, sounds do get distorted over long distance. That's only because the air distribution, right, could distort the sound, not because the different frequencies travel at different speeds. They travel at the same exact speed. So this side is a fixed quantity. So higher frequency and the lower wavelength will multiply into the same product, right? That's why I said higher frequencies. Now we should have lower wavelengths. We should be able to fit more half waves into the tube, except that increasing the frequency by a little bit like this, 430 to 480, we still couldn't really fit another half wavelengths, right? So we had less distances already. Instead of 58, 59, we have 52. Instead of the entire 1 meter, 87. That's what I got. So same exact calculation here. Take the third one, subtract the first one out of it. We have a full wavelength or 2 half wavelengths in between, right? So that's that. And once we get to C, I think it's a C4, but I'm pretty sure that's not a D4. It's too high. The frequency is too high. Um, because A5 is supposed to be twice this much, so that will be 800 something. So this is probably a D5. Someone with a computer, please Google it. See if D5 is close to 1,000. Anyway, so once we get to C4, we're able to fit more, right? We just barely fit. For me, I got 4 marks, so 3 halfway spacings in between the 116 and 80, 18 and 48, 48 and 17 is 9. Between 17 and 9 and the opening is just uncertain. So 1, 2, 3. 3 half waves, that's 1.5 wavelengths. So I take the 17 and subtract 17 out of 116. All right, here we go. So subtract the red out of the blue, and it's only 1/2 wavelength because there's 3 sections, 3 halves, right? So that's 1.5. And I got a slightly shorter wavelength. And for D5, I got all the way up to 7. 7 means 6 spacings in between, right? 6 spacings, that means divide by 3 full wavelengths. So I take the blue and the red, subtract the 2, divide by 3, and then divide by 100. All right. So I'll go through this rather quickly because I'm recording it, and also because after I'm finishing recording it, I will be able to answer individual questions, right? So that's how you would calculate one wavelength based on multiple locations, multiple sticker locations, right? So you basically just average out between the last sticker and the first sticker. So then why would you not just go last sticker and first sticker? Well, that's because you can easily miss stickers or locations in between. If you're just trying to get that last sticker position, you could have missed one and miscounted. And that would be a lot of error, right? Compared to what you might do just by putting the sticker slightly off from the exact location. All right, so that's the wavelengths, and the frequencies are calculated as inverse of all these frequencies stamped on the tuning forks. So they're relatively small because 1,000 hertz will be 0.001 in 1 hour frequency, which is period. So that's the last one. And I'll have to explain this d lambda. Maybe I should put a little space or underscore. D lambda, lambda is wavelengths. So we are measuring the wavelengths by putting stickers, at least half wavelengths. So how accurately were we measuring it? So I told you to try to vary the height of the movable piston and see if you can tell how much do you have to move in order to for the sound level to drop, so you can tell that you moved away from the optimal positions. So that is entirely up to you what you say your uncertainty is. So what did I say here? Um, Okay, so 0.005, that's 5 millimeters. So half of a centimeter. So that's a centimeter. So half of that, I think I was able to get that. That was my data from a decade ago. Maybe I'm getting older, I'm getting worse in my hearing. I might have to go 1 full centimeter. But for all of you, think about how accurately you are trying to vary. So go with that value. Say if you have a centimeter and you will go 0.001, that's 1 meter. So that's the uncertainty on the on your wavelength measurement. So I had them all the same because that's just me, right? I did it all myself. And let's see, this is DV. Let me grab the lab menu and start typing up some formulas. So, you know, the first page is description. All of a sudden, the second page, you have long formulas right there, right? So what exactly are those? The delta, the little fish was a not which is a it's like um, a tettle little thing there. It's called delta. That's a lowercase delta. Delta V equals a big square root times V. So what this is, it is actually telling you the speed of sound calculation uncertainty based on just one tuning fork with one wavelength and one frequency. So I'll type this up. This is what I'm calculating. Um, how about I do that? There we go. So V times square root. Oh, went all the way out of the formula editor. Okay, here we have a square root, and we have a square plus another thing square. Okay, so I'm just getting the structure out, right? Delta V, lambda first. Oh, there we go. See that? It's just getting there. Ah, there we go. Okay, so let's try to explain this. I'm going to scroll down a little so I have some space. Oh, come on, trying to grab it. Okay, so what exactly is this? This is the uncertainty of the velocity based on one tuning fork's measurement. So what exactly is this? This side is the uncertainty of the wavelength we measured, because the speed depends on two things, wavelength and frequency. So each will supply some uncertainty to the speed calculation. So our uncertainty in the wavelength is how well we can measure, right? Based on movement on the piston. So that is what I had, a half centimeter right there. And this wavelength is whatever wavelength we're talking about. Say we just want to talk about the A4, and we know the wavelength is 0.8 meters, and my uncertainty in the measurement is 0.005 meters. So that's how much it contributes to the velocity calculated based on these two values. Well, one value, the wavelength, and its own uncertainty. And this other one is how much uncertainty do I have from frequencies? Well, how do we find out frequency uncertainty on the tuning fork? Well, unless we have a very um, accurate apparatus and like an audio apparatus to measure frequency, but we can certainly deduce that from the number of digits that the tuning fork is supplying us, right? So this one has 426.7. So the frequency's uncertainty is plus minus that last digit 1, right? 426.7 plus minus 0.1. So let's where is it? Okay. So let me open up this formula. So be mindful, it's a little long. But let's watch. Here's a square root, right? Here comes one of the squares. Here comes another one of the squares. So this first square with the red over purple, red is the uncertainty of the wavelengths. I I estimated myself, right? Half centimeter. And then the purple is the wavelength itself. So we square that. And the other square is 0.1 over the green. 0.1 is exactly how much you can vary if you have a 1 digit after decimal accuracy, right? So that's a 0.1 hertz on top of 426.7. So that's where the 0.1 is, because I've observed there's a 0.7 instead of not having a digit after decimal. It did have 1 digit. So that's the uncertainty of the frequency. And if I open up this one here, it's slightly different because now I'm referring to a different wavelengths. And here I still have the same estimate for my uncertainty when I was varying the piston. But here, see that the frequency uncertainty now becomes 1 because I have 480, not 480.0. That's how they stated it. So that's how I would accept it as 480 plus minus 1. The last digit is the uncertain digit, right? So that's why I had a 1 here, and then divide by the frequency itself. So you can imagine this one will also have uncertainty of plus minus 1 hertz, plus minus 1 hertz, except the relative uncertainty, the fraction here, is 1 hertz out of 512, 1 hertz out of 1,000, right? Relative uncertainty is slightly less if you have a higher frequency, but same exact absolute uncertainty. So that's what I calculated out. And the D is a little less and less and less for higher frequency tuning forks, only because the uncertainty here is 1 hertz out of 1,000 hertz, right? This is 1 hertz out of 500 hertz. Anyway, so when you combine the squares and take a square root and multiply, let's not multiply that. So let's see, do I multiply? Yeah, I did multiply the speed. That gets you this cell. So let's see, let's double click that. Give me a second here. Double click this. So the speed is where I got the slope of the dots, which is the speed of sound. Because if you look at it, I have what um, wavelengths versus 1 over frequency. So if I rewrite this formula here, um, I'll get a second copy. So wavelengths versus, oh, okay, that's kind of odd. Okay, that's fine. I'll redo this. So okay, so wavelengths is this. Okay, so let's take a quick look. We have this formula to start with. We divide frequency out on both sides. So this right side will only have wavelengths, and left side will have 1 over frequency, right? So that's what this looks like. This looks like y equals kx, right? Y is wavelengths, and the x is 1 over frequency. The k, the slope of the line, is the velocity, right? Speed of sound. So that's what we're going after. So we plot out this as y, 1 over frequency as x, and we do a fit, and the result is we got 342. So we're using this as speed of sound in these calculations. Okay, so sorry, in these, mm, let's see, where's that? Okay, yep. Why is this? Let's see. Mm, the lambda. Okay, so the lambda dv. Okay, let's open this one up. So that's dv calculation. So I have basically referred to the same exact velocity for all these dv calculations. All right. So that's the value multiplied in the front. So calculate the velocity out based on the slope. You can either use Linus or you can observe there is the value right there, right? So you can do that. And we also have a very long formula of delta V, and that is a long expression of a large square root of 4 squares and then whole thing divided by 4. I know that's a little bit difficult to calculate, but well, if you just carefully calculate every single one of those little terms, then you should be able to do it. And then let's see, speed of sound expected. This is, well, the room temperature, we don't really have the exact room temperature. Our thermometer broke. So I had a 23 degrees C and I wrote down 25. 25 is a typical room temperature. A couple degrees of temperature difference will change this value by, let's see, about 4% of the 20% change. So it's a relatively small change. So you'll just use 25. You can use 25 degrees C. And there's also a speed of sound calculation. So a lot of these calculations compared to what we did last time. So we have this formula, speed of sound, 331 times, this is square root of temperature. Um, let's say temperature in C divided by 273. Oh, but then we have to add a 1 to it. This is because we're using temperature in degrees C, not in Kelvin. So a 25, right? And over here, so speed of sound, let's see, experimental, what is the room temperature? Okay, and the calculation is here. So let me open this one up to compare. Okay, I had a 332, so that's a 0.3% different from 331. Always do that, 331, and the 1 plus, um, let's see, why is this a 0.00? Oh, okay. So I think that's actually 1 over 273. I'm not sure why I multiplied. So let's just do a division like before. 273. Okay, divide by 273 or multiply by that small number. And that's the room temperature, which I'll change to, well, you can change to 25, but I collected these data with 23 degrees C room temperature. So I won't be changing that. So you hit that, you calculated the speed of sound. And here is what the speed of sound that you got experimentally. So between the two, um, let's see, delta V. So the delta V is, mm, let's see, my calculation is these for averaged. Okay, so instead of doing the whole square, I think I just did the four of these things averaged. And it's similar to what that value was. So a 2 and 342 plus minus 2 will certainly not cover 359. All right, so um, see that I only was able to confirm if I use the uncertainty of that slope, but that's only if I use a different value. Let's remove that. So one more time for the last part. So calculate the expected velocity based on room temperature, and that is the okay. This is the calculated value, and oh, I see. I know what it is. This didn't really get a square root. Yeah, 331 times that. Okay, that will actually be fixing it. Yep. I think I may have gotten rid of the 0.5 by mistake. Okay, so the 0.5 will be square root, right? So that will be the exact formula, but beside that. So 345. So 342 is experimental fit, and averaging all these gets you a 2. So 344 to 340 is the range. We almost, well, I almost proved it, but didn't. But if I look at the uncertainty of my slope, because the data points are not exactly along one line, that uncertainty gives me a range of 10. So 352 to 332, that does cover 345. So based on that uncertainty, I was able to prove it, but not on the uncertainty that we're supposed to be calculating. I think we'll just do this. We'll calculate these values, we'll average the four. Well, we'll not use the very large formula of averaging four squares and square root. So we'll average these four, and that is this value right here. And we'll compare that with the, um, basically the slope plus minus this value, compare that with the calculated speed of sound. And it'll be harder to prove because we didn't really have the exact room temperature, but that should be okay. It's practice anyway. Okay, so let me stop the recording.